I'll be good. Okay. Says I'm on, so I'll take it that I'm on. Okay, I'm going to jump quite quickly into this. This is the part two to the stream I did yesterday. When we looked at this paper, June 2018, paper two. We did the first 10 questions, so this is where we left on. Yeah, so we did this question last. Before we jump into the next question, I just want to briefly explain this because I did explain it last time. The best, uh, and it's the very start question. 1B. Okay, cool. So the range. Um, let me just write it. I don't know here. So the range of this function. Uh, um, so you had to basically observe will notice that this is a decreasing function, but it's quite tricky to see that, and it was when I went through it. But the explanation behind that is if you split this up into this fraction here, uh, which you obtain by dividing by x on both sides, notice that x is divided. This makes it a lot more clearer to see. And you should also then notice also 1 over x, as x gets bigger, 1 over x gets smaller because you are dividing by a bigger number, okay? And we saw this last time as well, right? So we notice what happens when you divide by bigger values of x, it goes to 0. And we're going to apply that to this as well. So when x gets bigger, so when 1 over x gets smaller, which again happens when x is bigger, when x goes to infinity, this numerator here has to get smaller because you are adding a smaller number as x gets bigger. 5 over x goes lower and lower and smaller as x gets bigger and bigger, okay? So you're dividing by a bigger number of x each time you increase it, okay? So 2 plus a smaller number, that means you're reducing the numerator as x goes up. On the contrary, the denominator increases or gets bigger as x gets bigger because you are subtracted by a smaller number. Okay, so 1 minus a smaller number means the denominator gets bigger over time. So what happens is the numerator gets smaller and the denominator gets bigger as increases to infinity, right? So what that happens overall is the fraction has to get smaller, right? Has to get smaller each time you increase x. And because this is g of x, that means g of x is decreasing because of that logic, right? So as x keeps getting bigger and bigger, the overall fraction gets smaller and smaller. So g of x goes down, so it's decreasing as x gets larger, goes infinity. So as x so here the overall fraction is decreasing. So what that happens is essentially, if you have two endpoints, then say this is g of x, it's not. It starts at 5, right? X is 5, and essentially it trails off to infinity, right? So in a weird way, you can kind of consider, I guess, infinity as the endpoint. But as I said before, infinity is a limit; it's not a number. So really, this is what's happening with the behavior of the function. It's decreasing. There's no spikes. It goes up and down. It just continuously goes down. So actually, the range overall, which is the graph of g of x, right, y values, it's the biggest at the smallest x value because obviously as x gets bigger, it goes smaller, as we just discussed. Okay, so x is 5 will give the biggest range, which is 15 over 2. And so the smallest value, well, gets smaller and smaller. So you have to consider when x is biggest. So when x goes to infinity, this actually goes to 2, which we discussed last time, right? It goes to 2 as x goes to infinity. So the limit, so the range possibly is between 15 over 2 and 2, right? So this is 2 and this is 15 over 2, right? So that's the range, right? And therefore the overall answer would be, well, x is between two, g of x, sorry, is between 2 and 15 over 2 because of that reasoning, right? Because it's decreasing and it's between 15 over 2 and 2, so it has to be in this interval, right? That's the range. And a final note, it's not 2 here. It's a strict inequality because it's a limit, right? It can't equal infinity. Nothing can be infinity. That's just what it goes to as x goes to infinity. But here we explicitly obtain 15 over 2 by substituting g of 5, okay, into the function because x can be equal to 5 here. Okay, I just wanted to start off with explaining that more clearly, but hopefully now you understand that. So that's the whole idea with range questions as well. You always want to consider if it's decreasing or increasing, and then what are the boundaries, right? Because if it's decreasing, it's going to go from the biggest value to the smallest value. So that will be your range. Okay. Okay, so I just wanted to start off with that to explain that more clearly. Because I didn't do a good job at it, I must admit. Um, but yeah, hopefully now we've got somewhere with that. Okay, now we're going to start with the other part of the paper. So we left off on that differential equation question. Now it looks like we've got some sort of partial fraction or division question. Okay, so we've got this fraction here, and it says to find the values of constants a, b, and c. You can do this two ways because they've given it this way. It opens two avenues. What you should notice is this is the degree of the numerator, so the highest power, is equal to the denominator, right? Because this is both a quadratic. So these are the degrees. When the numerator is equal to or bigger, no, sorry. Yes, when it's equal to or bigger than the denominator. Yeah, so the degree of numerator is bigger than or equal to the degree of the denominator, then you need to conduct you can divide it, right? You have to do algebraic long polynomial division, right? Long algebraic long division. Which is what's going on here. So one method you can do is, and I might do it both ways to show. Uh, the w- uh, the one that you probably expected to do is divide it, so divide the numerator by the denominator via long division. Or because they've given it in the form like this already, you can compare coefficients. So actually, what you could do, and this is one method, probably if you're not the most comfortable, but you really should be comfortable with algebraic division at this point. Uh, but you essentially could compare. It's like partial fractions, right? This is very similar to partial fractions. The method behind this. So combine this all as one fraction because this is equal to the left hand side is equal to the right hand side. So if you can write this all as one fraction, we can just simply compare. So that's one way of doing it. So I'll go over that. So I need a common denominator. So we need to times a by both the factors here. And then likewise plus b. Well, b's we just need to times by 1 minus 2x. Okay. Plus c, x minus 3. And that's all over x minus 3. 1 minus 2x. Notice this is now one fraction. And the denominators are exactly the same, which means the numerators have to be the same. And we can see this because this will give a quadratic if we expand it here, and we get a quadratic here. So let's just compare then. So you would get minus 6x squared plus 11x plus 1 has to be the same as a of the numerator bit, so a of x minus 3, 1 minus 2x plus b of 1 minus 2x plus c of x minus 3. Okay, okay, and now there's two ways of doing this. You can compare coefficients. So you expand the brackets, every bracket here, and you'll get a polynomial, a quadratic expression. Or you could just use substitution to pick, consider three different values of x. Okay, and I'm going to use that method. So the best way to do this is to work out, initially anyway, to only get one value, one number here, so we can easily solve it. To do that, say if we want c, we're going to want to set these two brackets to 0 to ensure a and b are eliminated, right? And the way to do that, well, there's only x minus 3 here, but there's but everything else is 1 minus 2x. So we need to set 1 minus 2x to 0 to make sure a and b are 0, so we can easily solve for c. So 1 minus 2x is 0. Well, 2x is 1, so x has to be half of that to happen. Okay, now we substitute it in. So minus 6 of a half squared plus 11 of a half plus 1 has to be, well, this will go to 0. So we're left with c of a half minus 3. Let's simplify that. Put that into the calculator. That's a minus 6, sorry, of a half squared plus 11 of a half plus 1. That gives you 5. Fairly nice number. 5 is equal to a half minus 3 is equal to minus 5 over 2c. Let's make that a bit clearer. Which therefore means c has to be what? Let's divide by 5 on minus 5 over 2. So you get c's minus 2. Cool. Again, we're going to apply that to the we're going to apply that sort of method again. So this time, well, a is not going to be easy to find a on its own because it has two of the factors. If you set either factor to 0, that'll get rid of a. So look at the single factors. So we did c. Let's look at b. So b is 1 minus 2x. Everything else is a factor of x minus 3. So let's set x to be 3. So then that means substitute that in. Minus 6 of 3 squared plus 11 of 3 plus 1 is equal to b of 1 minus 2x. So that's 6. And yeah, we put that in the calculator. Just hang on a sec. Okay, let's put that in. So you get minus 20. Okay, cool. So then minus 20 on the left-hand side is minus 5b. Okay. And then if we divide through by minus 5, that means b has to be 4, right? And so actually then all we need to find is a. And actually it's very easy to find a. Now let's come, because we can kind of mix it up. You can pick another value of x. Now, there's you don't want to set any of these to 0 because a will go to 0. So I guess the best way, yeah, actually, the best way to say let x is 0. Okay. So substitute that in. Well, 1. Every x term goes to 0 then. So just left with 1 equals a of 0 minus 3, which is minus 3. 1 minus 2x, that's 1. Plus b, when we know that b is 4, plus 4 of 1. Minus 2 of 0 minus 3, that's minus 3. And let's tidy this up a little bit. So that means 1 has to be minus 3a plus 4 plus 6. which means 3a has to be 9. Therefore, a has to be 3. Okay. Lovely stuff. I was going to say, alternatively, if you could just compare coefficients here, very quickly you should spot that a is the only this is the only way we can get an x squared term. So if you think very quickly, well, the only way I can get that is doing x times minus 2x, which should be minus 2x squared. So minus 2a has to be minus 6, which means a has to be 3. Which we've got here. So there's two ways of doing it. There's very many ways of doing that. Okay, so that means the fracture. There you go. So we found A and B and C. So that's part A. Alternatively, you could do algebraic division. Okay. So the fraction to repeat. This is alternatively. Okay. This is another way of doing it. The fraction then. Let's go back. Is 1 plus 11 minus 6x squared. And that's over. And you're going to need to expand this out, okay? This product here. X minus 3, 1 minus 2x. And that's going to be minus 2x squared. Plus 6x. Plus x, that'd be plus 7x. Minus 3, I believe. X minus 2x squared. Minus 3. Plus 6x. Okay, that should be right. So I need to copy minus 2x squared plus 7x, was it? Minus 6. And that's the other way around. It's 1 plus 11x minus 6. Okay, just to double check that's right. I did copy up minus 3. Oh, okay. Not minus 6. Okay, so this is the fraction. So we want to set this up for division. So again, like always, put the bottom number denominator outside the bus stop. And then put the numerator inside, but make sure it's in descending powers of x. Right? So start with the highest power and then go down. Okay. So with algebraic division, you need to times by a number that gets you from minus 2 to minus 6. That will be 3x squared. No, sorry. It's 3, but hang on. So you put a number here. Anyway, so you times by you want to times this by 3. You can you can tell that I haven't done this division now either. How long have I not done division since my A levels? Really? When was that? Like 7 years ago, 8 years? Oh my God! And I'm now trying to do this for the first time. It's 7 years. Thank God. We've got the other method as well. Okay. Okay, you're going to do 1 times this by minus 3, wouldn't you? Uh, no, you want to times by. Yes, because the idea is you want to eliminate x squared. So you want to times this by -3 to get 6, and then you minus f in here. I just don't know where the 3 goes. Is it up here? Or here? I think it's just here, isn't it? I think that's what makes sense here. Okay. So minus of, and that's -3, wouldn't it? Be minus 6x squared minus 21x plus 9, minus 9, no, plus 9. So they cancel. That's 21. 32x minus 8. Okay. But then there's no remainder. There's nothing to bring down here, so this is the final answer. So it's saying your final answer, so the fraction, so it's -3. Okay, which is weird because it's 3 here. Did we get our sign wrong? Yeah, we did, didn't we? Because that's x minus 3. No, which is 0 minus 3, 1 minus 2x. But, no, that should be fine. B of 1, which is 4. And then C, 0 minus 3, yeah, that's plus 6. Right, and because what this would be is -3 plus, uh, 32x minus 8 over x minus 3, 1 minus 2x. Something like that, if I remember vaguely the method. By the way, this is now waffle, by the way. I should probably move on, actually. But then you could split that into partial fractions, which isn't ideal, because now that takes a lot more work. Yeah, so that's split up into partial fractions, isn't it? But I'm confused. Why is a -3 here? Because by the method, you subtract whatever you get here. Oh, no. I'm stupid. I just don't know my signs. Yes, it is +3. Because if you times 3, you get -6x squared. Then this will be wrong as well as a result. This quotient here. Yes, sorry, just +3 because 3 is -6x squared. Because then you have -6, add 6, which goes to 0x squared. 11, and then that would be plus, and that would be minus 9. 11 minus 21, that should give minus 10. And 1 plus 9 will get you plus 10. So that would be 10x. No, 10 minus 10x, sorry. So that'd be 3, okay. So that's the thing here on top. And then you have the remainder, right? So this is the remainder term over the denominator, which is factorized again. And then you can split this into partial fractions. So again, let's just do that. Let's go all the way here. So 10 minus 10x over x minus 3, 1 minus 2x, which will be equal to b over x minus 3 plus c over 1 minus 2x, right? And again, you can compare them, bring them together, sorry. So b of 1 minus 2x plus c of x minus 3 all over x minus 3, 1 minus 2x. And likewise, now the numerator has to be the same as the numerator on both sides. So 10 minus 10x has to be equal to b of 1 minus 2x plus c of x minus 3. Okay, and now you do the sort of method again. So again, let's let each bracket equal 0. So first of all, let x equals 3. So therefore, 10 minus 10 of 3. Well, the c goes to 0. 3 minus 3 is 0. So b is b of 1 minus 6. Therefore, minus 20 equals minus 5b, which I remember is there, which means b has to be 4. Okay. Likewise, again, let b 0. So 1 minus 2x has to be 0. So x has to be a half. Therefore, 10 minus 10 of a half is equal to c of a half minus 3, which means 10 minus 5, which is 5, has to equal minus 5 over 2c, right? Yes, so that means c has to be minus 2, not 2, minus 2. And actually, those are the values we've got right. The b's 4, c's minus 2, if I remember correctly. Yes, here, and a's 3. So that's the alternative, and then obviously then you those are the values. So that's the alternative way. Obviously, you shouldn't be like me. I've not looked at algebraic division in like 7 years. That's the last time I did my A-levels. So you should be a lot more quicker on the pulse than this. But not bad going. Still got it, I think. But yeah, that's the sort of that's the process, right? Um, so there's two ways you can do it. You can directly, because they're giving you they're giving you it in the form it needs to be in. So you don't need to do the algebraic division. So you can jump right into combining the fraction, and then comparing coefficients, right? Or however. So you set the numerator on both sides the same, and then you can either substitute various values of x, or you can compare coefficients. It's up to you. But ultimately, that's how you can get the value, and I think that's the nicest way. If they give you this sort of question and they give you the form already with missing values, don't be afraid to just use what they're giving you. Don't like try, I guess, overcomplicate it or do extra work. You know. But the other way, and they don't have to tell you that, by the way. Really, they would expect you to know you can divide it, and then you can split it into partial fractions as so. But this is a bit more hefty work. But yeah, alternatively, spot the degrees on the numerator is on the denominator is equal. Okay, so that means you're eligible to use algebraic division, which we do here. Okay, and then you get 3 plus the remainder. And then you can split this remainder up into partial fractions to get 3 to then find b and c. Okay, but those are two ways you can do it. But let's have a look at part B. Okay. Oh, decreasing functions. Oh, there we go. We just did that earlier. So f of x is this again. So it's exactly the same function, and it says prove that f of x is a decreasing function. So, as I said, there were two ways to show it. Well, there's a way you can always show a function is decreasing without having to like manipulate algebra or reason and stuff like that. And that is a function f of x is decreasing. Oh, and it's decreasing for all values of x. If I can write this down. if f dash of x is less than 0 or equal to 0 for all values of x, okay? So in other words, if you find the derivative and you show it's always negative, then it's decreasing, okay? Now at A level, I don't think they're that pedantic about whether it's equal to, but there is differences. That is the proper definition of it. There is strictly decreasing, and that's a strict inequality. If it said strictly decreasing, then it would strictly have to be less than 0. But because it's just decreasing, it can be equal to 0. Okay. The whole idea is that as long as the function keeps going down continuously, that obviously that's going up a bit, but you know what I mean. As long as it keeps going down, then it's a decreasing function. But this is the way you show it, like I guess, like properly. I guess you should compute the derivative and then check the sign. Okay. And I guess that makes sense as well because what the first derivative is, uh, it's about the tangents, right? So if the first derivative is negative, that means the tangent has to be negative as well, which is how it happens, right? In order, if a curve is continuously going down, the tangent at all the points has to be a negative slope, right? So that's the geometric interpretation behind that. Anyway, I'm waffling a lot. So it said to find that f of x, no, prove that it's decreasing. But they told us in part A this factorization, not factorization, this alternative way of finding the missing values. So 3 plus 4 over, what was it? 3 plus 4 over x minus 3, was it? Yeah, x minus 3 plus c over 1 minus 2x. Minus plus c, which is minus 2 over 1 minus 2x. Cool. Why is that helpful? Well, first of all, exam technique. If they ask you to do something like that in part A, and then ask you another questions in part B, they're probably going to want you to use part A. Okay. But also, because we want to differentiate, the original function is a quotient rule, right? It's two functions of x on the top and the bottom. So it's a bit more work. But here, if we just say 3 plus 4 of x minus 3 to the minus 1, minus 2 of 1 minus 2x to the minus 1, is this just not simple chain rule? Right? So it like, makes our work a lot easier. So let's compute the derivative then. Well, a constant goes to 0 plus 4. So that's going to be 4 times by the derivative in the bracket. So x minus 3 just goes to 1. So that's nothing. And then times by the power minus 1. And then knock off the power. Likewise for this, minus 2. Again, the derivative of this is minus 2 times by the power, and then knock off the power. Then we can simplify it. So minus 4 of x minus 3 squared. And then, okay, we've got 3 negatives, so it's going to be a negative. Minus 2 times minus 2 is 4. 4 times minus 1 is minus 4. And that should be minus 2, not squared. Uh, okay. It might still be a bit unclear what this is. So again, let's use indexes to convert this to like a fraction that we can easily see. So that's going to be minus 4 over x minus 3 squared. Minus 4 over 1 minus 2x squared. And actually, hopefully you can spot now, this will have to be less than 0. It has to be negative, okay? And actually, it's actually it can never be 0 actually, so it's strictly less than 0. But either way, it's negative, right? Why is that? Well, how can you reason that? Well, obviously, as you can see, the denominator is squared on both of them, so the denominator is positive, right? It's a square number. But here, and actually, I guess actually, let's make this more clearer. Actually, let's put the negative on the outside. So the fractions itself is positive, right? A positive number on either side. But there's a negative. So actually, a negative times a positive is a negative. So the overall thing has to be negative. So I guess we could say since the fractions and 4 over 1 minus 2x squared are positive, since 4 and uh, since well 4 is positive. Clear, obviously. You probably don't need to write that, but I'm just being a bit rigorous here. Since 4 is positive and the denominators are square numbers. Okay. So if you have to prove it, you have to be a bit careful how you word it. Are square numbers. Since we are multiplying both fractions uh, by a negative, uh, by a negative, the overall function f dash of x must must be negative. Okay. Yeah, that's the sort of thing then. Okay, so hopefully it makes sense. Okay. Um, you could alternative state, I guess, like 4 is greater than 0. X minus 3 squared greater than 0. 1 minus 2x is greater than 0 squared, because they're square numbers. Therefore, the negative of this has to be less than 0. Okay, so you can phrase it as long as you get the idea that you recognize each of these parts is positive and it's overall negative. I guess you can make this clearer, right? And even clearer. A negative of, and factor a negative out, right? And then therefore this whole bit has to be positive, but it's times the negative. Okay, so hopefully it makes sense. So therefore f dash of x, and I should probably be clearer, less than 0 means f of x. So if the derivative is less than 0, like we said, the original function f of x must be decreasing. Okay, and that is kind of like the way I guess the computational way of showing a function decreasing. You know, I said in part one, like there are many ways of showing it can be decreasing, but that's probably the most formulaic way. But it's very awkward actually seen to like compute. Well, it's probably easily done, but it's still quite a bit of work to show that it's decreasing with the first derivative. So you want to avoid computing derivatives, but is there a way you can show that this is negative? I guess if you wanted to avoid it, you could complete the square of both of them, because they're both quadratics. And I assume one would always be positive and then one would always be negative. So then you can conclude it's negative. Oh no, sorry, decreasing. No, if it's decreasing, no, if you're not computing the derivative, you need to show that actually f of x1 is always less than equal to f of x2, uh, as long as x1 is less than equal to x2, and that's for every value of x. Okay, I'm going a bit of a tangent here, but that's what we mean by a function being decreasing. That if you plug in a smaller value of x, then the function will be a smaller value, right? No, so no. If it's decreasing, it's going from big to small. So x2 has to be less than x1. Because if we plug a bigger value of x, then it's actually getting lower than the so it's less this way around. So that's what we mean by a function decreasing. But like I said, if we think about tangents, if a function is continuously going down, the only way that can happen is if the tangents are also on the negative gradient. All right, it's negatively sloping. It's not going this way because that then like the gradients are positive. It means it's going up, right? By definition. So the slope's going down, then why the function has to be going down. Okay. Hopefully it clears it up. So yeah, they don't touch on that much in the textbook. Again, I might make a video on it at some point. I'll do a series perhaps of like going over all the topics. But that's what we mean by decreasing. Do not use this definition because it's very, very awkward to prove, especially for A level. But what you want to be showing is f dash of x is less than or equal to 0 for all x. Okay, so any value of x. But you don't have to worry about that. But as long as you show, if you don't pick a certain value of x, if you keep it general, then actually you are proving it as a result. As long as you show this, then it's a decreasing function. Don't worry about this. That's what it actually means. Okay. Okay, hopefully that's the explanation. Like I said, I'm not just going over the questions, but I'm going over the thought process and giving explanations. Whether or not I've done it, explained it well, is a different matter. But I'm trying my best to give an explanation for these questions. But hopefully that should be quite, that shouldn't be an unexpected question if we revised. Okay, but I'm doing more than just showing the method and being a mark scheme. But yeah, hopefully it made sense. Okay, one question 12. And these are very typical. We're going to have a trig proof question. Okay, so prove that 1 minus cos 2x, 2 theta is uh, identical to tan theta sine 2 theta. Okay. Um. Okay. So generally, you often want to start from the left-hand side, just for how to set up the question. But which side you want to pick to simplify is generally the side with the most stuff in it. So here, 1 minus cos 2x, not a lot to it. Tan theta 2 sine 2 theta is a lot more. So I think it actually might be best to start from the right-hand side this time, because it might give us something more to work with. And that's the idea. Let's start from the right. But yeah, let's do it. Okay. So again, you're gonna need to remember the identities, right? So tan theta is sine theta over cos. And that's the only one that's apparent at the moment. And obviously the double angles, well, you're gonna need to know that sine theta over cos theta. And you're gonna need to know that sine 2 theta is 2 sine theta cos theta. Okay, so that's going to be 2 sine theta cos theta. And, well, the cos thetas cancel out. So you're left with 2 sine squared theta. Okay, now, we can use this to guide us and actually should recognize this is immediately true. But because you should know the double angle for cos 2 theta as well. But what is the double angle cos 2 theta? What you should never do is work on both sides and then meet them. What you should do is start from the right hand side and fully show that you get the left hand side without manipulating it. You won't get the marks that way if you do a bit of both. Okay. What I'm doing here is a bit of rough working for the to see what this should come to, and then I'll do it for here. Okay. So cos 2 theta, you should realise is cos squared theta minus sine squared theta. Well, that's something we've got here. That's good. Well, actually, cos squared theta is 1 minus. Uh, Actually, I'm going to substitute that in there, actually. Well, it's sine squared theta. Well, if we rearrange it, it's cos squared theta minus cos 2 theta. And we're going to substitute that in there and double it. So that's going to be 2 cos squared theta minus 2 cos 2 theta. Okay. And then we're going to apply I'm going to move this down a little bit. Then I'm going to apply the Pythagorean identity, right? No, sorry, cos. Ooh, actually, no, I'm waffling. I want because what my method. Okay, I'm not explaining it very well. Okay, leave it there. So what I was going to say was, it's to substitute this in, but then we're going to have to use it again anyway for cos squared. Because what we're going to do is say that cos squared, wow, and that's the Pythagorean identity, right? Which is sine squared theta plus cos squared. Theta has to be 1. So then you rearrange that for cos. That's 1 minus sine squared theta minus cos 2 theta. Which means if you move it on the other side, 2 sine squared theta has to be 1 minus cos 2 theta. But this is where it gets awkward. We didn't do a lot of work here, especially for 3 marks, really. So would you get the marks from jumping from this to this? Again, it's kind of like what I'm doing here. You're working a bit from the left-hand side, aren't you? Here. We need to clearly show that this goes right to the left with no manipulation. So that's what I'm struggling with a bit here. I can clearly see the why that they're the same. That's great. But I need to prove it right, which is what the question is. So how should I go about doing this? Well, yeah, let's jump with what we did before. So we know that this is true. So that means sine squared theta is 2 lots of cos squared theta minus cos 2 theta, like we did before, okay? But now we're going to use the Pythagorean identity. No, we're not. Sorry, no, we're not. Uh, no, what we're going to do is we're going to reuse the cos 2 theta bit. Uh, no, hang on. Hmm. No, I'm going to say hmm, this would be cos 2. No, that's reusing it. So this would be 1 minus sine squared theta. But how would that help? Hmm. I could just immediately just jump to this, which is the left hand side, but it's about proving it, so it's a bit tricky. This is. How do I directly show that this is the same as 1 minus cos 2 theta? We know it is. We've just shown it, but obviously we've done a bit of work in here to get to that point. So we can't jump anything, because it's a proof. Proofs have to be quite explicit and clear, with no jumping missing steps or explanations. Which is tricky. Uh, hmm. Hmm. Uh, so what would happen if we use Pythagorean? It would be 1 minus sine squared. Ah, hmm. I really am tempted to jump to this, but we have to derive it a little bit. 1 minus sine squared theta minus cos 2 theta. But that wouldn't help, would it? Because there's now still a sine squared. But then we want to get rid of the sine squared, which is the whole idea. Uh, uh, I don't know. I guess what we could do is use this a little bit. I guess we could say, uh, well, that's going to be too long. I don't know. I'm going to jump right to it. I don't know. What I am going to do, as a learning, I'm going to check the marks scheme, see where the marks come from. Because I don't see how. I don't see where the marks are coming from. If it was only 2 marks, I'd be comfortable in doing this. But it's 3 marks, so what are they after for this? Um, Let me have a look at the mark scheme. Uh, Maybe I'm just overthinking it. uh, was it question 12? Was it? Yeah, okay. Okay. The first way they say tan theta sine 2 theta is this, which we've done. We cancelled out the cos. Oh, yeah. Get to this and to the. Oh, it's 3 marks. Okay. I was overthinking it then. Sorry. Ignore that last 5 minutes then of me waffling, trying to overthink it. Yeah, that's perfectly fine. As long as you realise this as well, that's perfectly fine to jump to. The trouble I was having was trying to make it as like rigid as possible. Trying to not manipulate the left anyway, but it's fine, I guess. They're having a problem with that. Because I was trying to find a way of like directly substituting cos 2 theta in terms of this and then rearrange, but it's a bit of a mess. But yeah, it's fine to just leave it as that. That's completely fine. Okay. So ignore that last part then. I was completely in my okay. That's waffling. I know that for next time though. That I don't need to do that much essentially. Uh, okay. And again, this is the good thing, right? We're going over the sort of thought processes, especially someone who hasn't done this for a while. So it's good to the stuff that sticks in your long term memory, I guess, and how you approach it. I don't know. It shows that you truly understand it, I guess, rather than just learning it. Not learning it. Well, you want to learn it, but like memorizing, like the methods stuff like that. So I think this is a good way of approaching the paper. I don't. I don't know. I don't know. Obviously, if someone finds me not useful, that I'm fine with that. Hopefully, it helps someone though. Anyway. Stop the waffling. Part B. So it says to solve this equation, right? A very nasty looking equation, which is also quite typical. So it says sec squared x minus 1 of, was it 1 minus cos 2x equals, not identical, equals. 3 tan squared x sine 2x. Okay. Okay. Look very nasty, but they told you part A for a reason. We know that 1 minus cos 2x is tan x sine 2x from part A. Is that right? Tan x. Yeah, yeah. Cool. So we can just substitute that in. Um, so sub into equation. So therefore sec squared x minus 1. And you can do it either way, right? But because this is explicit, we don't have to change anything. We can just, this is 2x, not cos squared. We can just directly substitute it in and see what happens. Tan x sine x is 3 tan squared x sine x. And you should notice we have common terms on both sides. So let's move everything to the left. Minus 3 tan squared x sine x equals 0. And we can factorize. When you're solving trig equations, you should never divide, okay? Always seek to factorize. Because when you're dividing, you're going to lose solutions, okay? So I could perhaps divide by tan x sine x, because you should notice that's a common factor in both of them. But I'm going to factorize. So I'm going to say tan x sine x of sec squared x minus 1 minus 3 tan x. And that's equal to 0. So I've not lost solutions, okay? Can I simplify this? I think I can. You should remember the identity. 1 plus tan squared x is the same as sec squared x. Well, I'm going to substitute that in then. So I'm going to say, therefore, tan x sine x of sec squared x, which is 1 plus tan squared. Well, 1 plus tan squared, but 1 minus 1 is 0, so you just tan squared, right? Minus 3 tan x equals 0. And then I can factorize even more, so I can say that tan x of tan x sine x of tan x minus 3 equals 0. Okay, we cannot do anything more of that, so let's equate each part to 0. So tan x equals 0, or tan x sine x is 0, but tan x is 0, or sine x is 0. But we already know tan x could be 0. So we're solving these two, or tan x equals 3. And like I said exactly in the first part, every trig equation should boil down to solving sine of an angle equals a number, a constant, cos of an angle is a constant, or tan of an angle is a constant. Now that's exactly what we've got here. Tan of an angle is 0 or 3, or sine x of an angle is 0. So that is what every single, and that's the idea of trig equations, is to simplify so it's in this form, okay? Now we can solve it. Cool. So tan x is 0. Very useful to sketch the graph. Also, what range are we working in? We don't need to adjust it because it's tan x. Between minus pi over 2 and pi over 2. Okay, it's a bit awkward. Okay, so that's what we're going to sketch it between. So minus pi over 2 to x to pi over 2. Tan x is 0. So it's going to have an asymptote at pi over 2. And therefore another asymptote at minus pi over 2. Oh, that's not what tan looks like. There we go. That's what tan x is. Okay. So tan x is 0 in this range. Well, there's only one solution. Uh, the solution is, well, x is 0, and you can do that by inverting. Okay. Um. Uh. If on your calculator, check right. So make sure the radians. So arctan of 0 is 0, but you should know your trig. Your exact values, right? Spot this on the graph. So x is 0. There'll be no more solutions in this interval. Okay. After pi over 2, it exceeds here, and minus pi over 2. So there's only one solution here. Likewise, tan x is 3. Since we've got the tan graph, let's solve the other tan one. 3 is going to be about there, right? 3. Wow, again, there's only one solution in this interval between minus pi over 2 and pi over 2. So therefore, we'll just do the arc tan of it. So arc tan of 3 will get you 1.249 radians, right? Does it say to how many decimal points? Give any non-exact answer to 3 decimal points. Oh, okay. Yeah, so 1.249. Okay. Okay, so that's two of them. Tan x is 0, tan x is 3. What about sin x? Again, let's sketch the graph between sine pi over 2 to minus pi over 2. So sin x would look like that for pi over 2. Obviously, that if we continued it, it would look like that. But we're only interested between minus pi over 2 and pi over 2. And that's the sine graph. Okay, cool. So I need it to be 0. Well, again, that just means x is 0, and that's the only solution in this interval. Therefore, x is 0 or 1.249 radians. And that should be your solution to that question. Okay, a fairly oh, hang on. Oh dear. No, we messed up somewhere. Again, probably wouldn't surprise me if we did a sign wrong or something. Okay, where did we go wrong here? So 1 plus tan squared is that is the right identity, isn't it? God, imagine I got the identity wrong. No, that's the right identity. Did I substitute it? Did I not substitute it in right? I bet that's it. So 1 plus tan squared minus 1. So the 1s will cancel. So you're left with tan squared x minus 3 tan x. That's not a plus 1, is it? Hopefully not. No. Oh, minus 5. We copied it down wrong. Oh, you're kidding me. Minus 5, not minus 1. Oh my god. Ah. Again, in my defense, I said in the other live stream, it's really awkward when you're on the computer and my screen anyway. Have to write it out on a digital pen and have to keep looking back and forth. You're bound to copy stuff down wrong. In the real thing, the question's right there. It's really nicely written. But it's so awkward on the computer. It really is. I do apologise for that, but we have to go for that again. So it's x squared x minus 4. I know it was a bit too easy, that was, for 6 marks. I know. I had a weird feeling that's why I double checked. So instead of minus 1, it's minus 5. My god. So my maths was right. Just fucking can't read. So x squared x minus 5. X squared x minus 5. Okay, let's substitute this in. Now this is going to be different. So you can have tan squared x minus 3 tan x. And then you're going to have 1 minus 5, which is minus 4. Okay, so that makes it a bit more complicated. Oh god. Bring this up again. Okay, oh for God's sake. See, computer's so awkward. Can't do what I bloody tell it to. Okay. So okay. So all of this is going to have to get rid of. Actually, oh no. No, we can use this bit. Tan x sin x. I believe. But we need to factorize this. So this is a hidden quadratic, right? If u is tan x, that's the same as saying u squared minus 3u minus 4 equals 0. That I believe should factorize to u minus 4, u plus 1. Minus 4 add 1 gets minus 3 times give minus 4. So that's the same as saying tan x minus 4, tan x plus 1 equals 0. Okay. Uh, is everything else right? It looks it. Okay. Okay. I forgot to say, bloody hell, this bloody computer. There we are. Ah, go away. Okay, so we've got this. Okay, so we've got this factorization. Again, this bracket has to be 0, which means tan x is 0 or sin x is 0, or tan x is 4, or tan x is minus 1. And again, it's the same sort of approach, right? So tan x is 0, but it has to give x is 0. Tan x is 4, so not 3. That would have to give. What's tan x is 4? Arctan of 4, which is 1.32. 6 radians to 3 degrees, right? Uh, no, sorry, tan x is 4, right? So x is 1.3 to 6 to 3 decimal places, or tan x is minus 1. So minus 1 would look here, right? So that'd be minus 1 here, that'd be 4. So that'd be there. Tan x is 0, tan x is 4, tan x is minus 1 would be there. Only one solution, each in the range. So tan x is minus 1 would mean x has to be the arctan it. Arctan minus 1 gets you minus pi over 4. Now that's exact, so you don't need to do anything with that. And actually, yeah, so we didn't have to do much to adjust it. So our final solutions, and then sin x is 0, is 0 minus pi over 4, 1.326 radians. Okay, and hopefully that should be the right answer this time. Oh, God. Uh, yes, x is 0, x is minus pi over 4, and x is 1.326. Cool, lovely, lovely stuff. Bloody hell, I just couldn't read the question. My math is on point, but I can't read the bloody question. Again, this is good exam practice, though, right? How many times I've just mucked up because I couldn't read the right number or got a sign error? Or not sign error. Well, yeah, I treated them positive or the negative and misread it or something. Ah, okay. There we go. Learn that for next time. But yeah, as I keep saying, though, it is quite awkward on the computer, but better than nothing, I guess. Anyway, question 13. Now, I want to address something very quickly with this type of question. You will not get a question like that. Well, you won't get a question that's 10 marks in one go. Since 2022, they have, well, they produced a document. So it's like a changes they made to the exam papers. And one of them is that they're splitting up questions. So there shouldn't be really more than 6 marks in a single part of a question, but this is 10. And that's one of the main reasons is that it put, especially students who might have messed up or feel a bit incompetent, but they could tackle certain parts of it. they'd be locked out with 10 marks, and realistically, they'd probably get like 3 or 4 out of 10 at least. So it's done to help the student. But so you won't get questions like this now, but that doesn't mean the question will remain, but they split it up. So you do certain parts. So like a 3 mark, a 4 mark, and another 3 mark, or something like that. So I just want to address that. So you won't get questions like this anymore, but it's still good practice. Okay. They could get an area integration question like this. So we'll go over it anyway. Okay. But don't freak out if it's big nasty 10 marker. You won't get questions like that in your exam. At least not in one go, anyway. Okay, so we've got out of the way. So we've got this area. Essentially, find the area of R using integration, right? So that's how you find areas. Is use integration. So how are we going to do that? Well, let's have a look what it tells us. Is we're given the curve here, which is y is x ln x. We are given the normal, which would mean that is perpendicular to the tangent at that point here at P. Actually, let's put it here. So it's tangent. That's what a normal is. A normal is defined to be perpendicular to a tangent at a point, okay, where the tangent is to the curve. Okay, so essentially, yeah, we need to find this. So there's a lot of information we need to find first. We need to find this point here. So if I call this x1 and I call this, well, this is E, right? E. They're giving us the intersection point. Quite nice of them. And then we find x2 here. Well, notice that the area is just going to be the integral of between x1 and E of the curve, right? Of x and x. It's because if you notice we integrate it between x1 and E, it's just the area under the curve, right, between the axes. So we can just integrate it between the bounds here. Then we can split this up, and actually, the second area, well, that's going to be this little triangle here. So it's going to be half times base, which is x2 minus E, times the height, which is again E, the vertical height here. So, or before we jump into it, and that comes from, just to clarify, E and then x2 minus E. Okay, that's the area of the triangle here. Okay, just to clarify what's going on. We'll talk more about that in a minute. But what we need to do is find this intersection point x1 and x2. So where the curve first crosses uh, x and x crosses the x-axis, and when this line normal crosses the x-axis, right? The intersect between the normal here and here with the curve. So that's what we're going to do. So to find x1, and once we find x1 and x2, we can find these. We can find this, okay? So to find x1, solve x ln x equals 0, right? That'll give you the intercept here. So that means either x is 0 or ln x is 0. But obviously, we know it crosses 0 here, so it can't be that. But we know x1 has to be above 0, right? Because we can see that it intersects here, which is across the origin. So therefore, ln x is 0, which means x1, which is x here. Well, what you could say it's e to the 0, right? Which is 1. If you raise both sides by ln e, so e to the ln x is e to the 0. You should know they cancel out. It's in the formula book as well. So you get x is e to the 0, which is 1. Okay, that's where that comes from. Okay. Oh, so that's how you can solve that. Lovely jubbly. So that's x1. Now to find x2, we need equation of the normal. because once we found the equation of the normal, we can substitute y0 to find x2. So we can find the missing x2, the root, right, where it crosses the x-axis. So y would have to be mx plus c. That is the same with every single line. That's the general equation. Okay. So gradient of normal is perpendicular to the gradient. No, sorry, the normal. Sorry, not the gradient. Just the normal is perpendicular to tangent at P. And P is EE, right? That's the intersection. That's where the normal is at P. Well, we need to find the tangent, right? So gradient of tangent. Well, that's going to be the derivative of x ln x at x equals E, right? So that's the point where the tangent is at E. This is P. So the tangent, well, the gradient of the tangent is the derivative at the point. Well, what is the derivative of this? So product rule, right? So differentiate the first part, which is differential of x, which is 1 times ln x, that's just ln x, plus x times ln x, which is, well, the derivative of ln x is 1 over x. So that's going to be x over x, which is ln x plus 1. Cool. So then, at x equals E, uh, gradient of tangent, well, that's going to be ln of E plus 1. Make sure that's an E. Okay. Well, ln of E is 1, and then 1 plus 1 is 2. You can put that into the calculator. Okay, so therefore ebb, which is gradient of tangent of the normal, that's going to be minus a half, right? Because that is perpendicular, and perpendicular means the negative reciprocal. So take the reciprocal of 2, which is a half, and minus it. So therefore y is minus a half x plus c. Now, how do we find c? Well, we can substitute a point in, can't we? And we know that this point P, E, E, lies, is on the normal, right? Because it's normal at that point. So sub the point EE into normal. So then you get E, which is minus a half E plus C. Well, that will have to mean C is 3 over 2E, right? 1.5E minus a half E gets you 1E. Cool. So therefore Y is minus a half X plus 3 over 2E. So X, so sub X, so then we want to find X2. Right, let's have a look again. Okay, X2, that occurs on the x-axis, right? So that's when y is 0, right? So we're going to substitute y0 to find x2. And that means 0 is minus a half x2 plus 3 over 2e. And that means that x2, so a half x2 would be 3 over 2, so that's going to be 3e, right? Cool. So now we found out missing information. So area then is between, what was it, 0? No, it was between x1 and E. X1 was, remind me what x1 was again? It was, x1 was 1, okay, so e to the 0. and that's the integral x ln x, plus, and it was this bit here, a half. So let's go back. So then, so that interval here finds the area between x1 and e before they intersect. So the area under the curve here. And then this next bit, it's a triangle, right? Formed by the line, the normal. And that is a half times x2 minus e times e. So it's a half times x2 minus e times, well, x2 minus e, well, x2 is 3e minus e times e. Okay. And we can simplify this a little bit. So e to the 1 of x ln x, dx, sorry, plus, and then, okay, well, 3e minus e is 2e. Half that, you get e, and then times by e, you get e squared, okay? So now our main mission is to just find what this integral is. And actually, you should hopefully realize what it is. So this is a product rule, right? Not product rule, by parts. And actually, you should know it's in the formula book, so you don't need to learn it. But the product rule, when you're integrating the product of two functions, is it's here, right? It's not. It doesn't say it's a product rule or anything. Well, it's here. So u of dv by dx, and you probably know this by now anyway. But I'm just going to go over it. So u dv by dx is equal to uv minus the integral of, I believe it's u du by dx v dx. Is that right? If I remember that correctly. uv minus the integral of v du dx dx. Okay. You can remember the product rule however you want to. Let's just say it's product rule. You don't need to write this down, by the way, in the exam. I'm just explaining it and showing you how to go through it. That's the product rule, so it's by parts. It's a product rule for integration. That's what I'm getting at. So that's by parts. Okay. So we have a product, but the question is, what do we let u and v? So we need to integrate v, because obviously v integrates here, and we need to differentiate u. Well, we don't really know well, you can integrate ln x, but it's a bit messy. Maybe. So I think when we have x ln x, we're not integrating ln x. Don't get this confused. I feel like a lot of people get confused with integrating ln x. And you should know that's also by parts, because you can say that's the integral of 1 times ln x, and then you integrate the 1 and differentiate the ln x. But we're not integrating ln x here. We're integrating x. Anyway, it makes sense to differentiate ln x because we know the derivative of that rather than the product or the integral. So we're going to let u be ln x. That's what we're going to differentiate, and v is what we're going to integrate. So that's going to be x. So that means u dash is going to be 1 over x, and v dash is this, so v, so that's v dash, or dv by dx, and v is going to be half x squared, right? Okay, so then, therefore, the integral of x ln x via this formula, if you substitute it in dx, sorry. Well, that's uv. Uv's here, half x squared ln x minus the integral of du dx, which is going to be 1 over x times by v, which is a half x squared. And that's going to be half x squared ln x minus the integral of, well, I'm going to take a factor of a half out, right? Half of the integral. Now, 1 over x times by x squared. You're just left with x. And this is why it goes nicely when you differentiate the ln x. 1 over x will cancel the x here. Cool. Now we can integrate that very nicely, can't we? That's a half x squared ln x. About minus a half of integral of x we just saw was a half x squared. So that'll go down to a half x squared ln x minus a quarter x squared. We don't need to bother with plus c because we're just finding what the antiderivative of this is. So we're finding what this function integrates to, but we're not concerned with a plus c, okay? Because ultimately this is a definite integration between limits, so the plus c will get rid of. Okay, so then that means the area is going to be the definite so we know that x ln x integrates to this. So we need to integrate this between e and 1. So we substitute e and 1 as our bounds here. So that's a half x squared ln x minus a fourth x squared between e and 1 plus e squared, right? Okay, let's integrate this then. Let's work this out. So we're going to have a half and substitute the top number in. A half e squared ln e minus a quarter e squared minus, and then a half of 1 squared ln 1 minus a quarter 1 squared plus e squared right at the outside. What does that simplify to? Well, ln e goes to 1, so this is just a half e squared minus a quarter e squared. And then a half of 1, ln 1 goes to 0. So this will go away, so you're just left with minus a quarter plus e squared. Okay, let's simplify this a little bit. Half, that'd be a quarter e squared, right? A half, 0.5 minus 0.25 of e squared plus a quarter plus e squared. And that'll be 5 over 4 e squared plus a quarter. Okay, so that's the area. What does it tell us to give our form in, our answer in the form a e squared plus b, where a and b are rational numbers. Yeah, we did that, right? A e squared plus b. That is a. So a is 5 over 4, b is a fourth, and they're both rational. So that is our answer here. I want to double check that because that's 10 marks. That is that could be bound to make an error there, but hopefully I've not done anything wrong there. Yeah, 5 over 4 e squared plus a quarter. Nice, lovely, lovely jubbly. That's all right. So yeah, that is the process of finding an area questions like that. Obviously, that's going to be integration. So you're probably going to need to work out the intersection points, right, in order before you integrate. But hopefully that makes sense of what we've done here. Also to note, if you don't realise this is a triangle, you can treat the line, the normal, as a function of x that you integrate. So what was the equation was of the normal here? Was it y minus a half x plus 3 over 2e? Was that it? You can integrate the area of the triangle here, which we found, is the same as integrating the line between the points. So that is going to be between e and x2. Now, x2 was 3e of the function, right, of half x minus a half x, sorry, plus 3 over 2e. If you are struggling to realise this as a triangle and what the area is and what that, you can treat this as another integral, right, between the limits of e and 3e, and you can integrate the line, okay, which is what we found here. Okay, so again, there's two ways of doing that, but yeah, that's the process. Just find the intersection point for the axis and then computing some integrals. So it's really just an integral question, essentially. Okay, question 14. This is, I believe, the final question. Here we are. Okay. A scientist is studying a population of mice on an island. Uh, yeah, this is the exponential modelling question. But here we are. So, number of mice 2 months after the study is modelled by here. Fairly typical. So, part A, find the number of mice at the start of study. Wow, that's going to be start of study is T0. So, that means N is going to be 900 over 3 plus 7 e to the 0, right? Substitute T0 in, you get e to the 0. So, that's going to be 900 over 10, which is going to be 90 mice. Uh, cool. There we are. That's a nice part A. Part B, show that the rate of growth is given by that formula. Okay. So again, it's just asking us to find the derivative. Not the nicest one, granted. There is two ways you can do this. Obviously, recognize it is a quotient rule. Obviously, there's a number here, so it's not that it doesn't matter. But actually, it's only one function, right, on the denominator. We could say that actually n is 900 lots of 3 plus 7 e to the minus 0.25t to the minus 1. And actually, therefore, then it just becomes a chain rule question. So yeah, so then dn by dt. So that's 9. So again, it's like the last question we did a few questions ago. Differentiate a fraction like this, okay? So 900 times by the derivative. Okay, so what's the derivative? So the constant will go away to 0. 7 e to the minus 0.25t. That's going to be 7 of minus 0.25 e to the minus 0.25t. Okay. And that'll be times by minus 1. Minus 1. And then times by same thing. 3 plus 7e minus 0.25t squared. Okay. They did tell us to show that, so if we get the right answer, then this is right. But anyway, let's simplify this. So you can have 900 of 7 times 7 times minus 0.25, which will be minus 7 over 4 e to the minus 0.25t. And that's going to be a negative outside. So that's going to be minus 900 because it times it by minus 1. And then that's 3 plus 7e to the minus 0.25t squared. Minus 2, sorry, minus 2. Okay. Now let's pull it all as a fraction. Let's get rid of this index here. So it's going to be minus 900. And then we can times this. We can times the minus 900 by the minus 7 over 4. So you're left with 1575 e to the minus 0.25t all over 3 plus 7e to the minus 0.25t squared. Okay, hopefully that's the derivative, and we can get the answer from this. So it's told us to show this, okay, n of 300 minus n. Okay. Interesting. So all the n's are on the top. Interesting. Okay. So it doesn't look too similar, unfortunately. But that's we're gonna use but we're gonna use this to guide us, right? The n, so n is this, so any exponential has to be, well, yes, it has to be on the top. Interesting. Okay. Interesting. Okay. Hmm. Okay. So how can we get rid of, I'll put this in the numerator. Okay, actually, before we do, let's do some rough joins, right? What does n of 300 minus n over 1 1200 look like? What does that look like? Let's substitute n in. So obviously n was, well, n's that, so it's 900 over 3 plus 7e. 3, 0.25t. Uh, okay. So that's the aim that we want to get to. So if n is on top, which means the e's here. Oh, well, yeah, this is, uh, say this is equal to 1 over 2, 1200 of n of 300 minus n. Um, well, n is this. Well, there's an e on the bottom. So yeah, there's an e on the bottom. So we might not be too bad there. So I think the so I think the best step is the next step is to actually factor out a 1 out of 1 200. Now that's going to be out of we have a constant of 1575. So let's times that by 1200 and we get this number here. We can get rid of it. 189,000. So it's 1,890,000. And then if you compute that division, you get 1,575. Okay. So now I've got rid of the number. So now I've purely just got e to the minus 0.25t over 3 plus 7e minus 0.25t squared. Okay. Interesting. Okay. I'm gonna bring the working over here. Um, Interesting. This will have to go away at some point. So I have to get 1 over 1200. Hmm. Interesting. I do think I did the derivative right, by the way, because if we got squared on the bottom, that's what we would get if we did the quotient rule. Because remember the quotient rule at the end, it's got g of x all squared. So that's kind of why it kind of makes sense here. But that's where the trickiness is, and this is why it's the final question. Okay, so what am I thinking now? Well, actually, this is just an e term on its own. We can just bring that. We could say that's the same as 1,890,000 over 1,200 of 1 over e to the 0.25t. So we turned it positive because if this is the reciprocal, we can just bring it to the bottom. And we could say that's times by 3 plus 7e to the minus 0.25t squared. And what we can then do is expand this out. So, uh, e to the 0.25t. So I'm just going to work simplifying this bit, right? So e to the 0.25t of 3 plus 7e minus 0.25t all squared. That's going to be the same as e to the 0.25t, and then we're going to expand this out. So 3, and then if that's squared, we repeat the bracket. 0.25t, there we are. So 3 times 3 is 9. 3 plus 7 lots of this, plus which is 21. And then we have another lots of this, that's going to be 42. 0.25t. And then we're going to times by 7e to this e minus 0.25t times by itself. So 7 times 7 is 49. And then if we're doing e to the minus 0.25t times by e to the minus 0.25t, if we times in, if we have the same base and we times them, we have to add them together. So that'd be 0.25 minus 0.25 minus another 0.25. That'd be minus 0.5, right, of t. Okay, now this is all times by e to the 0.25t, so we can just do that, okay. So then that's going to be 9e to the 0.25t plus 42. Now these will cancel, right? Because if we times them with the same base, we add in 0.25 with minus 0.25t. That will just be left with e to the 0. Okay, and that will be 1. So that would just be 42. 42 e to the 0, it should be 42. Okay, and then 49 e to the minus 0.25t. And that's what we're left with. Okay, so that's simplified. So what we need to do, so let's just bring this back in then. So dn by dt would be 1,890 over 1,200 of 1 over this. Okay, so 9e to the 0.25t plus 42 minus plus, oh god, plus 42 t. I made that more clearer, sorry. 49 e to the minus 0.25t. I'm potentially thinking there's a hidden quadratic here. Let me check if it's not. So the hidden quadratic, if you put u to be e to the 0.25t, this will be the same as saying 9 uh, uh, 9u squared plus 42u plus 49 equals 0. Check this, right? If you times this by 0.2 e to the 0.25t, this will get the quadratic. Okay, that's an exercise, I guess, to check. So you're left at 9, 42, and 49. Oh, it does simplify quite nicely, actually. And that simplifies to u minus 7 over 3 squared. That's what this factorizes into, which is the same as saying 3u minus 7. Okay. But I don't think that will help us, will it? Hmm. So this would factorise to 3e to the 0.25t minus 7 squared. This denominator here, because this denominator, and you can check this, it's the same as this hidden quadratic. With u is e to the 0.25t. But would this help is my answer. Well, yes, it does actually. So dn by dt is the same 189 over 1,200. Um, that is 1 over 3e to the 0.25t minus 7 squared, I believe. Because isn't that the denominator of n? Yes, that is denominator of n. 3 plus 7e to the minus 0.25t. Oh, it's not exactly the same, is it? Uh, because this is a um, positive 0.25. N is negative. Uh, uh, okay. Okay, what I'm thinking, and probably should have done this earlier, is I'm thinking of just expanding this out, right? Substitute n into here, and then eventually you should get our original answer, right, when we differentiate. My only concern is that allowed? Uh, well, yeah, because I guess you could work backwards, couldn't you? Okay, so I'm going to leave all that for now. I'm going to say note that. And I was thinking of doing this at the start. So note that. What was it? I need to put my charger in. Uh, okay. Note that. So we want to show this, right? 1,000, 1 over 1,200, n of 300 minus n. Substitute that in is equal to 1 over 200 n, which is 900 over 3 plus 7 e to the minus 0.25t. Is that right? Of 300 minus n, which is 900 over 3 plus 7e to the minus 0.25t. Is that the right answer? Is that the right? 3 plus 7e to the. Cool. Okay. Then we can bring the 900 out. So 900 over 200. That's 1 over 3 plus 7e to the minus 0.25t times by, then we're going to combine it. So we're going to say 300 lots of 3, which is 900, minus 300 times 7, which is, uh, yeah, 2,100. Just need to double check that. E to the minus 0.25t minus 900 uh, over 3 plus 7e to the minus 0.25t. And that will go to Um, 900 over 200. That'll be 3 over 4. Okay, to simplify that. 3 over 4 of. Okay, well, 1 over this. Well, this is the same, right? So we could say, and that's great actually, because we recognise that. That'd be over that squared. 900, 900 not plus 900 minus 900 is 0. And then you're left with minus 100 e to the minus 0.25t. And then we could bring that constant out. So that'd be minus 2100 times by 3 over 4. And there we are. I recognise that number. Minus 1575 e to the minus 0.25t. All over 3 plus 7e to the minus 0.25 t squared. Is that not the original result we got of the derivative? No? Let's double check that. So what did we get? So this was dn. Okay. Yes, it's the same, except there's not a negative. Which, to be fair, is quite a brand at this point. Did I copy it down? N of 300 minus n. Okay. Okay, so where's our negative then? Where have we gone wrong with the negative? So 900 times the derivative of this, which would be 0 plus 7 times this, 0.25, the derivative of this, which is just minus 0.25, of e to the minus 0.25t times by minus 1, because that's the power, and then you knock it down by 1. So, hang on. No, hang on. 900. So that'd be a negative, right? Negative 7 over 4. Uh, and then the times by minus 1, which is minus 900 of that. But then the negatives cancel out. So I've got 1575, but the answer is minus 1575. Why is that? Uh, this is the answer they've given us. 900, let's check this then. 900 over, yeah, n times 300 minus 900 over this. So that'd be 900 of minus 900. Oh, that's why. Because this meant to be plus. Because what I did here, yeah, negatives again, bloody negatives. Yeah, I only picked the first. So what I did here was times 300 by the bracket here, but I I only times the 3. So then I put the negative behind the 300 times 7e, which is what I've done here. But this should be positive. So then that would be positive. So then that would be positive. So that is actually our answer. So in exam conditions, obviously it take a bit of time. Which is dn by dt, which we calculated. Now it doesn't say prove that, it says show that, and it's not an identity. So hence dn by dt is 1 over 1/1200 n of 300 minus n. Okay, I think that's the best way to do it if you're a bit stuck. Um, yeah, it's not like a trick proof with like an identity. Uh, you can kind of meet in the middle, I guess. I think I'm going to check the mark scheme though. I don't want to give false information, but that is an awful way to simplify though. So yeah, essentially, ignore once I've got to this point, ignore what I've done after that. Okay, that's rough workings. Well, that is the best strategy, I think. If you're unsure where it's going, work out what they're giving it to you, and try and work with that. What do they say? So dn by dt is that um uh I'm trying to work out what they did in the mark scheme. Uh 900 times a quarter. Yep, okay. Okay, so you get two, anyway, if you're a bit unsure of the work that you're working out, you get 2 marks for working out the derivative. So that you're not lost much there if you couldn't work out the how to show that. Uh, okay. They also, yeah. So then they simplify this bit. So once you worked out the derivative, they did what I did at the end. So then they worked backwards and kind of manipulated this bit. So that'll get you another mark if you correctly simplified this bit. Um, yeah, and yeah, the work backwards. Okay. Yes, so yeah, that's perfectly valid. You can work backwards a little bit as well. So what I'm gonna do is I'm gonna get rid of all this mess. I should have done that at the start, to be honest. I was thinking about that, but I was trying to be a bit smart. Again, like I said, don't try to be smart in an exam. I was trying to like come up with a way so I don't have to work, expand like the n of 300 minus n. I was trying to be clever, but it's very awkward, as you've seen. But yeah, that's fine. The mark scheme does allow you to do that, so that'll be 4 marks for that. But as for timing, if you're a bit strapped for time in the real thing, um, just work with work with what the question's giving you. Don't try and like do stuff on you. Don't try and like be cocky and try to like what I've done here, and just try and factorize crazy stuff and stuff like that. And you struggle to see where it leads to. If the question gives you the answer like that, um, don't be afraid to just manipulate that and expand it to compare it to the answer. Okay. The only time you just shouldn't do that, like I said, is when you have a trig proof. Do not. But other than that, should be fine. It's taken a while to get rid of this. Okay, yeah. Okay. Get rid of this to make room for the other part of the question. Okay, so that was definitely the hardest bit, definitely, for sure. But yeah, so what you could do, to reiterate, work out the n by dt just like by computing it, then manipulate this, expand it out, and then you should get to the answer. So you can work backward in that sense. That's fine. You're not proving an identity, just trying to prove that this is equivalent. It's just showing that this can be given by it. Okay, so you can work backwards. Anyway, so it's saying the rate of growth, which is dn by dt, is a maximum after t months. So you have to be very careful here. Really, really, really careful what they're saying. So the rate of growth is a maximum. So what you do not do here is conclude that dn by dt is 0. You're saying that n, it's saying you're not saying that the rate of change is a stationary point. You're saying that the dn is maximized. Now, how do you what does it mean to maximize a function? Because this is a function, right? Because it's still in terms of n at the end of the day. So how do we maximize a function? Say we have f of x. Maximum is when f dash of x is 0, the first derivative, and the second derivative is less than 0. Okay, but it's saying that we want to maximize this. So this is almost a function in itself, or f of n. Because again, to go back, it's in terms of no, oh no, it's in terms of it is in terms of t, but I'm looking at this, so this is in terms of n. Okay. We could you could say in terms of t. Why not do it in terms of t? Be a bit more specific. F of t. We want to maximize this derivative, so we need to differentiate um, the derivative again, and this has to be equal to 0. This is not a maximum. If we then want to show it's a maximum, we need to differentiate it again. So this is a function of t. We need to differentiate it twice, which is a third derivative, which has to be less than 0. Okay. So that's what's going. So you need to pay attention to the word in there. The rate of growth is a maximum, not the growth is a maximum, because growth would just be n. Okay. No, sorry. Yes. No, not the rate. Not the rate of growth. Like I had the numbers. The numbers. The rate of growth. Is growing, not just the growth itself, but the rate of it. The rate is the maximum. So we need to differentiate it again to get the turning point, which will mean the first derivative is a maximum. Okay, so we need to consider uh, d squared n by dt squared. Okay, now again, you told us part B for a reason. So if this is dn by dt, so we want to, so we have dn by dt, which is n of, no, was it was 1 over 1 2000 of n 300 minus n, right? Yes. Okay. We need to differentiate this again. No, sorry, no, sorry. We don't need to do this. Sorry. Not necessarily. Yeah, let's call it f of n. No, I'm sorry. No, I'm not gonna. I'm not gonna waffle. Sorry, I'm gonna stop waffling now. I'll get rid of this. I'll stop waffling. I'm overcomplicating it. Essentially, what I'm saying, I'll reiterate what's going on here. So that's what it means for a generic function to be a maximum. We're saying n 300 over n. So we are saying that the rate of growth is maximized. So this is the rate of growth, and we need to maximize this expression here. So we need to maximize Oh, what have I done here? There we are. Okay, hopefully that's clear. So that means we need to consider the derivative of this, right? 1 over 200, 1 over 1,200, n of 300 minus n. Hopefully that's clear, right? So, let's differentiate it then. Therefore, d over dn, because we're going to differentiate this back to n to differentiate it, of 1 over 200 n of 300 minus n. That's going to be, again, you bring the constant out, and then that's going to be, well, you can expand this. Well, that's the same as saying 300n minus n squared. Differential, that's going to be minus 2n plus 300. And we need to set this, and a maximum means that this has to be 0, right? Equals 0, which then means n has to be 150, right? So minus 2n plus 300 is 0. So 2n is 300, so n has to be 150. Which kind of makes sense with the question, right? If you pay attention. Okay. To verify it is indeed a maximum, because it could be a minimum, we don't know. Well, actually, no, we don't need to do any testing, do we? Because look at part A. Part A, the initial number was 90 mice. If part, if this is a minimum, that would have to be smaller than 90. But it's not, it's 150, so it's bigger than 90. So this will have to be a maximum by default, because it's the only turning point as well. So it can either be a minimum or maximum, but it can't be a minimum. So I guess let's reason that a little bit. But if you're unsure, you can differentiate again and substitute it in and show that the second derivative of this is less than 0. But I'll just say this must be maximum and maximum as it is bigger than 90 when obviously n is 0. No, 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 that's wrong. Because 90, no, 90, n is 90, that corresponds to the, what's it called? That corresponds to the original function. What we're differentiating here is not the original function of n, which is what, 900 over 3 plus 7e minus 0.2 by t. That's not what that's what the 90 is referring to. This is not 90 here. This 90 is not the original here. We want the maximum of these are different functions, is what I'm saying. So the maximum of this function here is not going to be the maximum here. Okay. So we do need to verify it is a maximum. I do apologise. It's somewhere. I think it would be better if I did it in my own time first and then explained it afterwards without any like mistakes. But I think this is a good. This is raw. I feel like it shows the natural working out. Anyway, so we need to verify this is indeed a maximum. So differentiate again, and you don't have to write in worded sentences like this. But I'm doing it here. Just explain what's going on. Okay. Anyway, so we need to differentiate again. So let's differentiate again. So d over dn of this 1 over 1 200 of minus 2n plus 300. Well, that's going to be 1 over 1 200 of, and then we differentiate, that's just going to be minus 2. Now that is going to be less than 0, therefore must be a maximum. Okay, so what did the question say? So there does exist a maximum. So it says find it's maximum after t months. Okay, so we need to find t, not n. Therefore, n is 150 is the maximum. But we need to find t. So remember, n is 900 over 3 plus 7 e to the minus 0.25 big T, because that's when the t is this, that's when n is 150. We need to solve for t. God, this question's never ending, man. It really is. Actually, no, you might be fine with that. No, it tells you. No, it tells you it's a maximum. Yes. Sorry, you didn't need to do that. That's just extra work because there's only one turning point here, and it tells you it's a maximum. So you don't need to do this bit. Sorry. But it's good to show this, I guess, actually. But I'm going to get rid of this now. You didn't need to do this bit because it already tells you it's a maximum, and we know there's only one stationary point. Therefore, it has to be a maximum by default. So hopefully that's clear. But yeah, they didn't take too much work though, so we didn't miss out on much. But I need to make room to solve this equation here. Okay, so what we're going to do, we're going to solve for t here. So again, like any ordinary fraction, we times across. So we say that 3 plus 7e to the minus 0.25t. Now that's going to be times by 150 to get 900, but then we divide by 150. Okay, so that means 7e to the minus 0.25t. That's this division here, which is 900 divided by 150, which is 6 minus 3. That'll be 3. Therefore, t, if you log both sides, so I'm going to make that clear actually. I'm going to say ln of 7e to the minus 0.25t equals ln 3. And what you can do here is move it on both sides. So you could say minus 0.25t is ln 3 over, because if you have raised it to the power, actually no. No, that's not right. Hang on. No, if it's raised to the power, it has to be for all of it. Well, if you times and sum it, that's the same as saying ln 7 plus ln e to the minus 0.25t equals ln 3, right? You can split this up using log laws, right? You should know that ln of AB is ln A plus ln B, okay? So if you add in two logs, you can bring them in and times them together. So that's what we've done here. We've split this up. So therefore, minus 0.25t is ln 3 minus ln 7. Okay, so we subtracted ln 7 to both sides, and then ln e, well, again, we can bring the power outside, because you should remember the log rule. Ln of a to the b is b ln a, okay? So you can always bring powers to the front. Okay, so, and then ln a is 1, so minus 0.25t is that, so that means t is going to be uh, minus 4 ln 3 minus ln 7. If you divide by minus 0.25, and that And that answer is going to be uh, t is learn 3 minus learn 7. You get 3.389 something months. So what does it say? Do we have to give it to a certain degrees, a certain degree of accuracy? Sorry. After t months. Yeah, so it's after 3 months. So after 3 equals 3 um, when rounded to the nearest decimal, to the nearest integer. So therefore, t is 3 months. Okay, because it says after 3. So it says after t months, but 3.389 is after 3, but it's before 4. So t has to be 3 there. So it's the first month after 3. Hopefully that makes sense there. That's a these are you can see why it's the final question. My God, part B and C are bloody rough, I must say. Okay, that's the whole bulk of the paper. Let me check that's right actually before we go further ahead. Oh, no, you don't need to round down actually. Sorry, you just treat it as that. Of course you can. You don't need to round down actually. That's the right answer, but you don't need to round. Well, you can. Uh, no, that's the answer. Sorry, I didn't need to round down. I don't know why. Oh well. That is the right answer. There we are. Or we could say 3.4. Okay. Yeah, it doesn't. Yeah, it doesn't need to be an integer. Sorry. I misread that. My apologies. It's not going the best, is it? I do apologise. But yeah, the whole bulk of it's right though, pretty much. But yeah, I do apologise for that misunderstanding there. Maximum after t months. It doesn't have to be integer, right? You can have 3.4 months. It would make it clear if it had to be an integer. So yeah, apologies for that. Okay, now for one last mark, we've got 99 out of 100. Let's get the last one. According to the model, the maximum number on the mice is p, and it's a state the value p. Now, there's two ways of doing stuff like this. I'm going to write it on here. I'm not going to. The two ways of finding the maximum. The again, like the computational way is doing the derivative, setting it to zero for the turning point, and then differentiating again and finding the maximum. So dn by dt is 0, so the maximum number of mice. And then yeah, and then differentiate again. But actually, we already know the first derivative. So that means n of 300 minus n has to be 0 because we found that in part B. So that means n has to be 0 or n has to be 300. But this is the minimum, clearly, because clearly 0 is going to be the least value. So 300 has to be a maximum, right? So n for p is 300 here. That ironically the hardest question, but that's probably the easiest mark out the paper at the very end there. Like I said, like even if you can't do another exam tip, if you cannot do the earlier parts of the question, you know, don't be put off by the later parts. You never know. You might be able to do it. Okay. This bit you didn't really need to do any work in. The question gave effort for you there. It set everything up. So all you need to do is because well, the turning point is 0, so it has to be any value of this is either minimum or maximum, but any 0 has to be a minimum. Clearly, 0 is the least amount of mice you can have. 300. Well, we know that was 90 at the start, so 300 has to be bigger. So it has to be the maximum value of n you can get. So therefore, the maximum has to be 300. Okay, I'm gonna leave that there then. Uh, okay, that was a rough last question, but that's why it's the last question. But yeah. Oh boy. But yeah, I'm gonna leave that there then. Again, if there are any questions for this, there probably will be. I don't think I did the best in that. Uh, but hopefully after and all that, like I said, this is the thought process, right? I could just be a mark scheme and tell you, you got to do this, do this, do this, do this, do this, do this, without explaining any of the thought processes or where you can go wrong, and how you get out of a sticky situation, like I did. Like I got into a little mess with the NDT, but then I thought, oh, well, let's just simplify and work with this, and then actually get the answer quite nicely. So that's the whole aim of this. Yeah, it might not be perfect, but exams aren't perfect, and that's the reality. I'm not going to be sitting with marks in there just explaining how well, just giving you the mark. You need to get a mark for this, mark for this, mark for this, and giving up no and not being like involved as such. But yeah, so that's the aim for that. But hopefully it all makes sense now. Okay. And yeah, that's 2018 paper two. So yeah, that's 2018 pure paper. For the next time at A level, we'll probably do another past paper. But yeah, I'm actually going to do some further math stuff now because obviously the further math exam on Monday. If you are watching in current time, stay tuned because in a few minutes I'll be doing further math paper one, June 2023, which I heard was an interesting paper. But for maths now, I'm going to leave it there. So again, any questions, let me know. But other than that, I'm going to leave you with that. So that's the whole paper done. There we are.